Okay, hi, welcome back. In this section of 11.2, we're going to talk about another counting technique called the combination. And this tends to be one of the more difficult aspects of this chapter for students, is telling the difference between when a situation calls for using a permutation and when it calls for using a combination, because they are two very different situations. So when we want to talk about combinations, order is not important. When we talk about permutations, order is important. So an example of a situation where order is not important, let's say electing 5 class representatives. The position of representative is the same, so if we talked about our student council being made up of 5 representatives, and we do Alice, Bob, Chris, Derek, and Elaine, that's the same thing as the same student council as if we elected Elaine, Derek, Chris, Bob, and Alice. It doesn't matter the order in which those people are elected because their positions are all the same. Order didn't matter. Now contrast this with electing like a president, vice president, secretary, treasurer. Here, these 4 positions are different. So the Alice is president, Bob is vice president, Chris is secretary, and Derek is treasurer, is a different student council from Derek is president, Chris is vice president, Bob is secretary, Alice is the treasurer. Even though it's the same 4 people, they're in different positions, so that makes a difference. So that's kind of a classic example of a situation that sounds like kind of the same situation. We're just electing people for a student council, but depending on what the details are, whether those positions are different or not, kind of dictates whether order was important or not, and whether we should be using a combination or permutation. So that's just a little example, and we'll look at some more specific examples and talk about whether we should be using combinations or permutations later on throughout this chapter. So we'll get more practice at that as we go, but that's a pretty standard example. So the formula for a combination, which we denote as, I guess we should say combinations of n objects, take n r at a time. So we do that, abbreviate that with the symbol NCR, and that's n factorial over n minus r factorial times r factorial. So the only part of this formula that's different than the permutations is this extra dividing by r factorial, which is basically getting rid of all the extra repeated. So that's going to get rid of the class, like the sets of representatives that are the same 5 people, but just like in a different order. So that's all that's doing there. So if we wanted to do then like 10C5, we can do that on our calculator. So if you go and press the math button, oops, I guess I should start with the 10, and then press the math button, go over to the probability menu, click the command 3 for NCR. Oops, I pressed the wrong button there. So math, probability, command 3. I must have pressed 6 there or something. And then write 5, and that's how we do that. You could plug it into the formula, but boy, that seems a lot easier to just use the built-in calculator function. Okay. So let's look at some examples of situations we can count using permutations. Okay. A standard deck of cards has 52 cards, 4 suits with 13 cards in each suit. Right, those 4 suits. You have hearts, diamonds, spades, and clubs. Okay. If the order in which 5 cards are dealt to you is not important, how many different 5-card hands are possible? So again, if you're playing cards against someone and you're sitting in your hand, you have like ace of hearts, 2 of clubs, 3 of spades, 7 of diamonds, and like jack of hearts. This is really the same hand as if you had 2 of clubs, ace of hearts, 3 of spades, 7 of diamonds, and jack of hearts. Because you have the same 5 cards, the order doesn't really matter when you're playing cards, because you can just pick and choose whichever card you wanted to use, right? So this is why it's a combination. Why order doesn't really matter is these are really the same hand, right? Okay. So if I want to do this, we've established that it's a combination. So I'm going to use NCR to count it. So how many cards do I have to choose from? Well, we said there's 52 in the deck. How many cards are going to go into my hand? Well, that's 5 of them. So I'll just go to my calculator and do 52 C5. And rather than going back through there, I'm going to just press second and enter to recall the last thing. And I can just go back and edit that 10 to be a 52. So I have 2,598,960. Okay. How many hands are all 5 cards the same color? So I guess it's worth pointing out to here, hearts and diamonds are red in color, and spades and clubs are black in color. If you haven't spent time playing cards, we'll do a lot of kind of card questions in this section. So if you aren't familiar with what kind of a deck of cards looks like, if you have one out, it could be helpful to you. So here we have 2 things that we have to take care of. We have 2 choices we have to make. We have to pick a color, and then we have to pick 5 cards from that color. So there are 2 possible colors. We need to choose one of them. And then inside of that color, we're either going to have hearts and diamonds. So there's 13 hearts and 13 diamonds, so 26 red cards. Or we have black cards. We have spades and clubs. There's 13 spades and 13 clubs, so 26 black cards. So regardless of which color we picked, we'd have 26 of that color, and we have to choose 5 of them. So if I go to my calculator, I'm going to do 2 math probability NCR, choose 1, times 26 math probability NCR, choose 5. When I do that, I get 131,560. Okay. Let's look at another example that doesn't involve playing cards, or some other examples that don't involve playing cards. We'll do a couple of different ones. So Shakespeare he wrote 38 plays. Bet you didn't know that. There were 18 of them were comedies, 10 are histories, and 10 are tragedies. So how many different sets of exactly 2 comedies and 1 tragedy can you read? So first things first, we have to think about if these sets of 3 plays represent a combination. So if I read comedy A and comedy B, and then tragedy A, that's the same thing as reading comedy A, tragedy A, and then comedy B, right? The order in which I read these 3 plays doesn't really change the set. Right? They're still reading the same 3 plays. The order in which I read them doesn't really matter in the context of this question, since there's no distinction between the order in which we're reading these implied in the question. Okay? So, what we need to do is pick 2 tragedies, and then pick 2 comedies, and then pick 1 tragedy. Okay, so we have 18 comedies to pick from, and we need to choose 2 of them. And then for the tragedies, we have 10 tragedies to pick from, and we need to choose 1 of them. And because we have to do one then the other, we need that multiplication, just like the kind of the fundamental counting principle. So I'll go to my calculator and type this in. So I'll do 18 math probability command 4. Oops, I meant command 3. C2 times 10 math probability command 3. Choose 1. When I do that, I get 1,530. Part B, how many sets of at most 3 plays can you read? So at most means 3 or less, right? So we could read 3 plays. We could read 2 plays. We could read 1 play, or we could read 0 plays. So to read 1 play, or read 3 plays, excuse me, that's 38. Choose 3. Again, there's 38 plays to choose from. We need to choose 3 of them. Then for 2 plays, that's 38, choose 2. For 1 play, that's 38, choose 1. And for 0 plays, that's 38, choose 0. And we're going to add those 4 things up to get the total number possible. So 38, math, probability, NCR, 3, plus 38, math, probability, 2, plus 38, math, probability, NCR, which is 1, plus 38, math, probability, NCR, 0. I do that, I get 9,178. Okay. Let's just do one more combination, or one more problem, and we'll call it a day. A basketball team is scheduled to have 12 home games. You want to attend at least 3 of them. How many different combinations of games can you attend? Okay. So, first things first, we know this is a combination question because it asks for combinations. But if you thought about it also in the context of this question, if you wanted to attend at least 3 games, if we're doing exactly 3, whether you attended games 1, 2, and 3, or you went to games 10, 11, and 12, doesn't really matter. Each of those satisfies 3 games. So like which games we attend doesn't really matter. Just the total number of games that we've attended kind of matters. So here, definitely the order doesn't matter. Like which games, there's nothing special about any given game. So if I want at least 3 of them, so we'd have, so that's 3 or more. So if we did 3 games, we could attend 4 games, 5 games, 6 games, 7 games, 8 games, 9 games, 10 games, 11 games, or we could go to all 12 games. Jeepers creepers. So this would be 12C3, 12C4, 12C5, all the way down to 12C12. And then we'd be adding up all of those to get our result. So, okay, that's fine. So again, we'll just get out our calculator. Do 12, math, probability, NCR, which is 3, plus, and then I'm just going to repeat that same process just a whole mess more times. Choose 4. Choose 5. And we're going to, when I do that, I got 4017. Now you might be asking yourself, isn't there an easier way to do that? That was a lot of exhaustion there. If this was at most 3, where I only have to add up 4 things, not a big deal. What's more difficult is a situation like this where we have to add up 9 things. Like, that's a lot of combinations to type into our calculator. Well, there is a easier way of thinking about this, and we can do this kind of by doing exclusion. So at least 3 is equivalent to not at most, or I should say not less than 3. And less than 3 is the same thing as at most 2. Since these games are discrete objects, less than 3 would be 2 games, 1 game, or 0 games, right? Which is the same thing as at most 2. Okay? So what do we have here? Well, for each game, we have 2 choices to go or not, right? So game 2, we have 2 choices to go or not. So out at game 12, we still have 2 choices to go or not. So 2 to the 12th possible attendance schedules, right? So that's all the different possible ways we could attend these 12 games. Going from going to none of them to going to all of them and everything in between. So what I need to subtract from that then is this situation where we go to at most 2 games. So if we go to 2 games exactly, we don't want those in there. Go to 1 game exactly, we don't want those in there. And we go to 0 games exactly, we don't want those in there. But every other schedule we want to keep, because those are all at least 3 games attended. This is a lot more realistic to type into my calculator. It takes me way less time, although it doesn't really matter. Either one of these approaches are perfectly reasonable, and there's no penalty for using one versus the other than like your fingers are going to get a little tired because you have a lot of combinations to type into your calculator, but I'm not too worried about your fingers falling off or anything. You guys are all strong, healthy individuals. So, and you see we get exactly the same thing, 4017. So, that wraps up everything I wanted to do with combinations. You guys should now be able to complete assignment 2, and good luck.